Dear students, welcome you all to the first class of this semester. This is semester 4, and in this semester you'll be doing one paper of physics, that is physics 04T, atomic, nuclear and solid state physics. As for me, I'll be taking unit 2 of the syllabus of this paper that has to do with nuclear physics. So unit 2, as you can see, all of you must have got a copy of the syllabus. So it has to do with nuclear physics. So the topics, if you go through the syllabus, is review of nature and radioactivity. So it has to do with radioactivity as such, some part of which you must have studied in your higher secondary classes, mean life and its deductions, then the basic ideas of alpha, beta and gamma decay. Then we have to talk about the interaction of gamma rays with matter, how the gamma rays they interact with matter as they pass through it. So it can induce different kinds of effects. We'll study all of these: photoelectric effect, Compton scattering, and pair production. Then we have different applications of radioactivity. We'll be talking about those applications: radiography, radioactive tracers, radioactive dating, that includes carbon dating. Then we'll go over to something called the particle accelerators. These are devices which can be used to accelerate particles to very high energies. So different kinds of accelerators are there, which we'll be covering during the course of this semester. Linear accelerators, cyclotron and its limitations, betatron and synchrotron. We'll study about these three kinds of accelerators: the linear accelerators, the cyclotron, and betatron and synchrotron. That apart, we'll be talking about the particle detectors, which can detect different kinds of particles and radiations. These are the ionization chamber, the GM counter, and the scintillation counter. We'll be talking about those. Next, we'll go over to artificial transmutation of elements. Then we'll talk about nuclear reactions, nuclear reaction energy, discovery of neutron, properties of neutron, etc. Then after that, we'll go over to something which is very interesting: nuclear fission. What is nuclear fission? The energy released during fission, and how this fission chain reaction can be controlled in nuclear reactors. And we'll be talking about the different types of reactors. After nuclear fission, we have another interesting topic, the nuclear fusion. This is the kind of nuclear reaction that occurs in the stars. After that, we'll be talking about the different nuclear models: the liquid drop model, the shell model, the collective model. Details we are not talking about here. We're just going through the topics of the syllabus. So as we reach these topics, we'll be discussing about them. But at this level, we'll be just talking about the basics of these topics. Then we'll be talking about the binding energy, calculation of the binding energy. After that, we'll come to the last topics of the nuclear physics part that we'll be doing in this semester. These are the cosmic rays and elementary particles. We'll discuss about the general characteristics of cosmic rays. Then we'll be talking about the classification of elementary particles. So at this level, we are not expected to go into the details of these topics. It will be kind of an introductory session or introduction to some basic topics of nuclear physics. So as you have seen, the first topic that is there in the syllabus is natural radioactivity. So as I told you, we are talking about nuclear physics. So what is nuclear physics basically? So we can define nuclear physics as a branch of physics that deals with the study of the nucleus, its properties, and its interactions. So before we go into nuclear physics, we need to know what is a nucleus. It may seem trivial because all of us know that matter is made up of atoms, and the atom has its own internal structure. Structure is such, it has a core, which we call the nucleus, surrounded by the orbiting electrons. So the nucleus is the core of an atom. So as per the standard definition, it's the core of an atom in which almost all the mass and charge of the atom is concentrated. So basically nuclear physics is the study of the nucleus of an atom. So the nucleus has its own properties, physical properties. We can talk about its composition. The nucleus is composed of the protons and the neutrons. Together we call them the nucleons. So it is composed of the protons and neutrons. So now that we are studying nuclear physics, we'll together call them the nucleons. We use a new term called the nucleons. So as per this terminology, the protons and the neutrons, we can say they are the same particle which exist in two charged states. So these are elementary particles. Later we'll be talking about them also. So we call them the elementary particles. So a nucleus is basically composed of the protons and the neutrons. The protons are positively charged and the neutrons are neutral. So this makes the nucleus a positively charged entity. So when we talk about the charge of a nucleus, this is just a kind of a revision that we are doing. When we talk about the charge of a nucleus, we know that the nucleus is positively charged. So how much positive charge will be there? It will be the total positive charge of all the protons that are present in a nucleus. So we usually denote a nucleus. If I have a nucleus, let me say if I have an element, X, and a nucleus of this element X, it has, let me say, Z protons and, let me say, N neutrons. So the total number of protons and neutrons in the nucleus, we call it the mass number, that is equal to Z plus of N, and this is known as the mass number of the nucleus. So these are some terms that you will need to remember and understand from now on. We call it the mass number, the total number of nucleons in the nucleus, that is the total number of protons and the total number of neutrons. They together form the mass number. It's called the mass number of the nucleus. And the number of protons inside the nucleus is called its atomic number. So as I told you, if we have a nucleus of an element X having mass number A and atomic number Z, we use a notation A, X, Z to represent this nucleus. This is the notation that is used to denote the nucleus of the element X having mass number A and atomic number Z. So for this nucleus, the charge of the nucleus will be Z times the charge of a proton. We are talking about the nucleus having Z protons. So the total positive charge of the nucleus will be Z times the charge of a proton. Now the charge of a proton is the positive A charge is equal to the in magnitude to the charge of an electron, but opposite in sign. So the charge of a proton is 1.6 into 10 to the power minus 19 coulomb positive charge. This is positive. So the total charge of the nucleus will be Z times the charge of, if I denote it as E plus. So Ze plus. Z is the number of protons. Composition, protons and neutrons, the charge is this much, and the mass, of course, the total mass of the nucleus will be the sum total of the mass of the protons and the neutrons. Of course, it is less by a certain factor, we call it the mass defect. We'll talk about it when we later on discuss about the binding energy of the nucleus. So basically, the mass of a nucleus is almost equal to the mass, sum total of the masses of the protons and the neutrons. Of course, it's less by a certain factor, we call it the mass defect. This is because when nucleus is formed from its components, a certain amount of mass is converted into energy and released in the process. We call it the binding energy of the nucleus. We'll talk about it more later. So the mass of the nucleus will be in magnitude comparable to the mass of the nucleons times the mass number. Dimension, the size of the nucleus. We know the atomic dimension for the atom. The dimension is around 1 angstrom. We call it 1 angstrom. This is 10 to the power minus 10 meter. So compared to that, this is the atomic dimension roughly. So when we talk about the nucleus, it's much smaller than that. For a nucleus, the dimension is of the order of 10 to the power minus 15 meter. We call it 1 femtometer. We call it 1 FM. So this is the some of the physical properties of the nucleus we are talking about. Then the next physical property that we can talk about is the density. So as we discussed already, as I have told you already, the nucleus is the core of an atom where almost all the mass of the atom is concentrated. And the dimension of the nucleus is very small, 10 to the power minus 15 meter. So you can imagine the density is mass per unit volume, right? So the density will be very high for nuclear matter. So it has been measured experimentally. The density of nuclear matter is of the order of 10 to the power 17 kilogram per meter cube. 10 to the power 17 kilogram per meter cube. If I convert this into centimeter cube, it will be roughly around 10 to the power 11 kilogram per centimeter cube. So you can imagine the amount of mass that is there inside the nucleus. 10 to the power 11 kilogram per centimeter cube. So if I have a block of nuclear matter, let me say a piece of chalk, something like this. 1 centimeter cube means a block having each side equal to 1 centimeter. So if I have this size of nuclear matter, its weight will be 10 to the power 11 kilograms. So you can imagine the amount of mass that is stored inside the nucleus. So that makes the nucleus very important, because we know Einstein's mass energy relation, E is equal to mc square. So if mass can be converted into energy, so if I have more mass, we'll get more energy. So basically it means nuclear matter, if it can be converted into energy, the amount of energy that we'll get is huge. It's just a simple example that I'm giving you, the importance of the nucleus and its study. So what we are talking about here is the topics that are there in the syllabus also. We are talking about trapping or extracting the energy stored inside the nucleus. So we are talking about the nuclear fission, and nuclear fusion, two reactions via which we can extract the amount of energy stored inside the nucleus. So this is another physical property, the density of the nucleus. Then the shape of the nucleus. By and large, we consider the nucleus to be spherical in shape. However, heavier nuclei, slight distortions are there from the spherical shape. So that is all about the shape of the nucleus. Then binding energy, I was hinting to this. Binding energy is the energy with which the components of a nucleus are held together to form the nucleus. In other words, binding energy is the amount of energy that you will need to supply to a nucleus to break it up into its components. So this is something which we'll be studying again later. So the binding energy of any nuclei gives us a measure of the stability of the nucleus. So this binding energy can be calculated. So during the formation of a nucleus, as I told you, an amount of mass is lost in the process. So it simply means if Z protons, say, and N neutrons, they come together to form the nucleus, and the protons, they have mass, let me say mp, and the neutrons, they have a mass mn. So the total mass of the constituents will be Zmp plus nmn. Z protons, each proton having mass mp, and n neutrons, each neutron having mass mn. Together they form the nucleus. But what is found is that the resultant nucleus that is formed will have a mass. Let me say M nucleus is the mass of the resultant nucleus that is formed, is found to be slightly lesser than the sum of the mass of the constituents. So this amount of mass, that is Zmp plus nmn minus of the mass of the resultant nucleus, we call it the mass defect, del m. So what happens? During the formation of the nucleus, this amount of mass is converted into energy and released in the process. So this amount of energy that is released in the process, del mc square, this is Einstein's mass energy relation. This amount of energy released during the formation of the nucleus is called the binding energy of the nucleus. So these are some basic properties of the nucleus. So what has been found is that almost all nuclei, they have a positive binding energy. That means that all the nuclei are stable entity. You will need to supply energy to the nucleus to break them apart. So it simply means inside the nucleus a special kind of a force operates, which we call the strong nuclear force. Why? Because inside a nucleus, as we know, protons are there. These protons are held together within the small dimension of the nucleus. The protons are held together within the small dimension of the nucleus, and all these protons are positively charged. So there will be electrostatic forces of repulsion, and the electrostatic force of repulsion we write as Coulomb force, that is proportional to Q1 Q2 by R square, where Q1 Q2 are the charges. So if I say I'm considering two protons, so this force will be proportional to E square, where E is the charge of the proton, positive charge, by R square, where R is the distance between the protons. Now we are talking about the nuclear dimension. The nuclear dimension, as I said, it's around 10 to the power minus 15 meter. So this is very, very small. That means R is very, very small. So Fc will be very, very large. The Coulomb force of repulsion will be very, very large. So in a nucleus, it's not that only 2 protons will be there. Heavier nuclei, there will be more number of protons. For example, say we are talking about 12C6 carbon nucleus. It has 6 protons. Mass number is 12. Then 235 is a heavier nuclei, uranium 92. So 92 protons held together within the dimension of the nucleus, uranium nucleus. So dimensions of the order of 10 to the power minus 15 meter. So the Coulomb forces will add up. As a result, the nucleus should have been very, very unstable because Fc becomes very, very large. So if we consider only Coulomb force or electrostatic force, we can't explain the stability, extreme stability of nuclei of atoms. So theory is that these nucleons inside the nucleus are held together by a special kind of a force which is called the strong nuclear force. Strong nuclear force. So this is a special kind of a force which is very, very strong, which is independent of charge. Independent of charge means because of this force, a proton and another proton will attract each other. Irrespective of the charge, it will attract each other. So this strong nuclear force gives rise to the stability of the nucleus.